In this video, we will talk about matrix inverses and their properties. We've already hinted that the matrix equation AX equals B can be solved with the inverse matrix of A, which we denote with this A to the minus 1, so that the solution to this AX equals B matrix equation is X is equal to A inverse times B. And this solution holds if and only if A has an inverse, which is if and only if A is non-singular. In this video, we will identify the identity matrix and then the matrix inverses here. And then we'll continue with properties of matrix inverses and then relate how these matrix inverses relate to linear systems. We will start with the identity matrix denoted with I subscript n. N is the number of rows and columns that the identity matrix has, and it's always a square matrix, so we only need n. Also, often the identity matrix is understood what n should be, so often it's just written with an I. But anyway, the identity matrix has zeros in all the entries when I does not equal j, and when I equals j, the entry is equal to 1. So here is an example. It has ones along the diagonal, all the other entries are 0. So we have this theorem, the INA equals AIN, which is equal to A. So this is kind of the summary of my theorem. So if B is an M by N matrix, then IM times B equals B, and B times IM equals B. In particular, if A is an M by N matrix, then IN times A equals AIN, which is equal to A. It seems like a lot of work to identify this identity matrix, but you have to remember that since matrix multiplication isn't commutative, technically you have to show both INA is equal to AIN, and actually that's mostly it. So here we are. And I have this example for you. Let's say A is equal to the matrix 1, 2, 0, negative 1, 3, 4, 6, 1, 8, and B is equal to the matrix 2, 3, 1, 1, 5, 7. C is equal to the matrix negative 2, 0, 8, 3, 6, 1. And X is the column vector 1, 0, 3. And just a note, I3 is equal to the identity matrix, that's 3 by 3, which there's 1 when I equals J. In other words, when we're on the diagonal, all the other entries are 0. And this is fairly straightforward. I will multiply I3 times A and show that it is equal to A. So here's my I3 matrix, my identity matrix, and my A matrix. So I have 1 times 1, my 0 times negative 1, and my 0 times 6. Remember, we're going row times column. So I just did the first row times first column here. For my next entry, for my first row, second column, I do my first row times second column. So 1 times 2. 0 times 3, and then 0 times 1. And then over here for my third column, or first row, third column, first row, third column, 1 times 0, 1 times 0, 0 times 4, and 0 times 8. So you can see what the effect of this 1, 0, 0 is it's picking out the first entry. Here it's picking out this 1, here it's picking out the 2, and here it's picking out this 0. And you can verify the rest, and you can see that it equals A. And then technically I should have done A times I3, but instead I just did B times I3 to show you this is a different size matrix, but here's B and here's 3. And the important thing is that this row goes across 3, and we can multiply times the column, which goes down 3. So we have 2 times 1 plus 0, so that's our 2. And then we multiply next row column, 2 times 0, 3 times 1, and then 0, so we have the 3, the 2 times 0, 3 times 0, 1 times 1. Here we're for the second row, we're doing the second row here, first column, so we have the 1. This will pick out this, here we have 0, 5, 0, and then we have 0, 0, 7. So this is equal to B. And then I have I3 times C, and again, it's a, here I have my 3 going across, multiplied by the 2 down, and you can verify it's equal to 0. And then I3 times my vector x. Again, it's 3 across with 3 down, so I can do this as well. So I have my 1 times 1 plus 0 is 1. I have my 0 times 1 is 0, plus 1 times 0 is 0, and 0 times 3, so that gives me the 3. And then I have 0, 0, and 3, and that is equal to x. And you also want to note I3 times b, because you have 3 going across but only 2 going down. It's mismatched, so it is not defined. Same with c times I3. It is not defined because you have only 2 across but 3 down. And just a couple of other notes before we go into matrix inverses. We often just write I as opposed to IN, and also note that IN, now that I said we just wrote I wrote IN, is equal to E1, E2, EN. So these are column vectors. E1, E2, and EN are column vectors, where E1 is the unit vector. So it's the vector with 1 in the first row. This is the vector with 1 in the second row, and this is the vector with 1 in the third row. And just to be explicit, this is E1. It has a 1 in the first row, and everything else is 0. E2 has a 1 in the second row, everything else is 0. E3 has a 1 in the third row, everything else is 0. En has 0 all the way up to the nth row, where it has a 1. And these are called our unit vectors because they're length 1, and they just basically represent all the directions. Now that we have the identity matrix defined, we can define matrix inverses. The n by n matrix B is the inverse for the matrix, the n by n matrix A, provided that AB equals BA is equal to I to the n. And here's an example of matrix inverses. I have A here is equal to 1, 2, 3, 4, and B is equal to -2, 1, 3/2, and -1/2. So when I multiply A times B, you can follow the calculations and see that I get I2, the identity matrix. And then because matrix multiplication is not commutative, technically I need to multiply B times A. And you can see I also get I2, and therefore we say that B is the inverse of A. This next example, let A equal 1, 2, 3, 6. Show that A has no inverse. We haven't even defined how to find the inverse, but what we could do is let's just assume that B is the inverse, and B has entries A, B, C, D. So B has to be 2 by 2 to be an inverse. So when we multiply 1, 2, 3, 6 times A, B, C, D, these are the equations we get. We get A plus 2C is equal to 1, B plus 2B is equal to 0, 3A plus 6C is equal to 0, and 3B plus 6D is equal to 1. So looking at this first equation, and then looking at the second equation, both of these equations involve AC, you can see that it's not possible to solve this system of equations. In other words, there's no AC combination that solves both of these, therefore A has no inverse. And you could have chosen to look at BD, so you could have taken a look at B plus 2D equals 0 and 3B plus 6D equals 1. And that probably also has no solution. But really, all you need is this part to say there's no solution, no inverse. Next, we have a theorem that says matrix inverses are unique. So if B and C are both inverses for the matrix A, then B equals C. The proof is fairly straightforward. Let's assume B and C are both inverses of A. So A times B equals B times A equals I, and A times C equals C times A equals I. But therefore, B is equal to B times I, which is equal to B times AC. And then because matrix multiplication is associative, that's equal to BA times C, but BA is equal to I. So that's I times C, which is equal to C. So what we have is B is equal to C. This is a proof you should be able to do. And actually, I should have mentioned this earlier. There are many proofs that I don't do, or many theorems that I just state without proof. So when I do a proof of a theorem, generally it's something that is important enough that you should be able to derive it yourself. Okay, so since we have proven the inverse is unique, we can denote the inverse by A minus 1 without confusion. And then also calculating the inverse of an n by n non-singular matrix will be covered in the next video. But we will look in this video at how to calculate the inverse of a 2 by 2 matrix. So let's say we have a 2 by 2 matrix A, which is equal to A, B, C, D. And we're going to set this delta equal to the AD minus BC. then if delta does equal 0, then A does not have an inverse. But if delta does not equal 0, then the inverse is given by 1 over delta. So again, if this were 0, this would be undefined. But if it's not 0, then it's 1 over delta times D minus B minus CA. So what you do is you swap the positions of A and D, and then you just put a negative on B and a negative on C. So without the delta notation, it's just 1 minus A times D, or 1 over A times D minus BC, dA swap, and B and C get negatives. Our first example, let's say A is equal to 6A, 3, 4, then delta is equal to 6 times 4 minus 3 times 8 is 0, which means A has no inverse, right? The 1 over delta would give us something undefined. If we have B equals 1, 7, 3, 5, then delta is equal to 1 times 5 minus 7 times 3, which is negative 16. So B inverse is going to be 1 over 16, negative 1 over 16 times, we're going to swap these two, so we have 5 and 1, and then we put a negative on these two, so negative 7 and negative 3. And we can confirm this inverse by multiplying B times B inverse. And you could also do B inverse times B, but I was lazy and only did one. Here is my B, here's my B inverse. I did the multiplication, and I get the identity matrix. Next, we have properties of matrix inverse. So if A and B are n by n matrices, each of which have an inverse, then A inverse has an inverse, and the inverse of A inverse is just equal to A, kind of what you would expect. AB has an inverse, and AB inverse is equal to B inverse times A inverse. And this proof is interesting, and it's kind of comes out kind of nicely. If K is a non-zero scalar and Ka has an inverse, then the inverse of Ka is equal to 1 over Ka inverse. And last, A transpose has an inverse, and A transpose inverse is equal to A inverse transpose. This proof is kind of interesting too, but it does fall out nicely. So the proof of part 1 is we want to show that A inverse has an inverse, and it's equal to A. So we're going to multiply A inverse by its inverse, which is A, and we're going to do both multiplications, and we'll see it's equal to I, because of the definition that AI is actually the inverse of A, but it's true the other way around too. So by definition, A inverse has an inverse, and it is A. That is, A inverse is equal to A. Part 2, so we'll look at AB, and we'll prove that the inverses of AB inverse is equal to B inverse A inverse. And what we have to do is just multiply them together. So we have AB times B inverse A inverse, but now because multiplication is associative, we can do the B times B inverse multiplication first, and we get A inverse. But this AI is just equal to A, so we have A times A inverse, which is just equal to I. So B inverse A inverse is the inverse of AB. And similarly, you would do the other multiplication as well. Part 3 is left as an exercise. And part 4 is to show the inverse of A transpose. And it is equal to A inverse transpose. So to prove that this is the inverse of A transpose, we'll multiply them together. So I have A transpose times A inverse transpose. So by properties of transpose, when you have two things multiplied together, their transpose is equal to C transpose A transpose. So their transposes separately, but you have to change the order. So here, that would mean this is A inverse transpose. These two are equal by this property here. And then A inverse is just the identity. Transposed is just the identity. Similarly, you can do it, switch the order for commutativity, and you'll see it's equal to I. And therefore AT has inverse A inverse transpose. These properties are really useful for other proofs, so make sure that these are things that you can call up pretty easily on your own without having to reference notes all the time. So here we have an example using these properties of matrices, or matrix inverses. So let's say A is equal to 1, 3, 2, 4, and B is equal to 3, negative 2, 1, negative 1. We want to calculate A inverse and B inverse, and then calculate AB inverse. And then we also want to show that AB inverse is not equal to A inverse times B inverse. Remember, when you take the inverse, you have to change the order. So this would be B inverse times A inverse. Anyway, so A inverse is equal to, doing that cross multiplication, we have 4 minus 6, and then we switch these two, the 4 and 1, and we put negatives on the other two. And so we finally get negative 2 3/2, 1 minus 1/2. Similarly, you can see B inverse is equal to 1, negative 2, 1 minus 3. So now to calculate a B inverse, I could have multiplied A times B and then use that same formula on AB, but I wanted to demonstrate this theorem. So AB inverse is equal to, by this theorem here, B inverse A inverse. So I have B inverse here, which is 1, negative 2, 1, negative 3, and A inverse, which is negative 2 3/2, 1, and minus 1/2. And you can see when I multiply everything out, I get, for my inverse matrix, minus 4 5/2, minus 5, and 3. Now I can confirm this is the inverse by multiplying this by AB, which I didn't do here, but once you multiply this times AB, A times B, which I also don't have calculated, you should be able to get the identity matrix. But one thing I did want to confirm, because this problem asked me to, is to confirm this is not equal to A inverse times B inverse. So here I have A inverse times B inverse, and you can see that the resulting matrix is not equal to AB inverse. So this video is a lot about calculations, although these properties are really good to know too for future proofs. Anyway, the next thing we want to look at is how these matrix inverses help us solve linear systems. And we have this theorem. If AX equals B is the matrix equation that represents an n by n system of linear equations, suppose A has an inverse, then the system has unique solutions given by X is equal to A inverse B. So we'll do a proof of this. And to see X is equal to A inverse B is a solution, we're just going to plug it into the equation. So we'll plug this, A inverse B, in for X. So I have AX equals B, we're plugging in X equals A inverse B. So since this matrix multiplication is associative, I can move the parentheses over. So I have A inverse, which is I, times B equals B, and of course I times B is just equal to B. And I'm done. Here is another proof that you should easily be able to replicate. And our first example, I have a set of linear equations, x1 plus 3x2 equals negative 1, and 2x1 plus 4x2 equals 2. So A is the 2 by 2 matrix, 1, 3, and 2, 4. So A inverse, again, I have my 1 times 4 minus 3 times 2. So that will give me minus 1/2. And then I also have these two swap trade places, and then these two become negative. So finally I get for A inverse minus 2 3/2, 1 minus 1/2. Now X, again, is equal to A inverse B. So I have my A inverse here, and then I plug in my B, and my B is equal to negative 1, 2. And so my final answer is 5, negative 2. That's equal to X. And I can verify my solution by multiplying A, my matrix A, times my vector X, and I verify what I get is equal to B, my negative 1, 2. And then also, I can, if I want, I can further than verify it solves the system of equations. So x1 is equal to 5, x2 is equal to negative 2. I can plug it into my equations, and you can see that this x solves both equations. A couple of other notes. So AXB has the solution x equals A inverse B only when A is a square matrix and it is invertible. But also a note, from a computational point of view, to solve the system of equations, Gaussian elimination is generally more efficient. So we are done with the main topics of this video. First, we define the identity matrix, and once we have the identity matrix, we define matrix inverses, and we found that they were unique. But if a matrix A times B is equal to B times A is equal to the identity matrix, then B is said to be the inverse of A. We talked about these properties of matrix inverses, and then also, so in particular, The inverse of A inverse is equal to A, and the inverse of AB is equal to B inverse times A inverse. The inverse of A transpose is equal to A inverse transpose, and the inverse of K times A is equal to 1 over K A inverse. And last, we talked about matrix inverses and linear systems, and this is the big important theorem. So let AX equals B be the matrix equation for a system of linear equations. Suppose A has an inverse. So again, this is a big, this is one of the conditions. A has an inverse. Then the system has a unique solution given by X equals A inverse times B. Here are 3 problems for you to try for review. So you can pause the video, give them a try, and on the next slide, I'll have solutions for you. This is the solution to the first problem. The solution to the second problem. And the solution to the last problem. And that's it for this video. Thank you for watching.